So first off, are there any questions that anyone has from between Tuesday and today? Anything that's come up? One question that came up at the end of class was due dates. And so let's take a look at our schedule. So our schedule shows all of our due dates. And I have the homework. I know pedagogically it's not the best strategy, but I got so sick of really good reasons to extend homework for people. And it's like every week I was extending it for like 6 different people, for good reasons. And so I'm trying it this year to have it all due right before the exam, which is terrifying to me because I was a student, my kids are just finishing college. It's so easy to move and operate on deadlines. But as a college math student in these upper level courses, Cal 2, Cal 3, Physics 2, you gotta stay on top of everything or you fall in a hole quickly. So I've left the trapdoor open. I don't want you to fall in it. So you should, as soon as we are done with a section, you really should be finishing that homework, within 48 hours. So we finished 6-1 on Tuesday, so ideally you've finished the 6-1 homework by now, but not having the stuff due every week means I'm gonna have to prod you and you're gonna have to stay self-motivated. You have to be a real college student. You gotta stay on top of it. Which is an important skill to learn because once you get to 4-year schools, a lot of times you are left to your own devices and you don't have the thing every week being required. So homework will be due. I have it in here listed as Tuesday night, ideally to give you a little bit of time to be just studying for the exam and not doing homework at the last moment. So it's due on Tuesday, the exams are on Thursday. Now the homework in a class like this, if you're not getting 100% on the homework, you are not doing enough work. Because you can do each problem as many times as you need. You can always regenerate after you miss it 3 times. Like the homework and the quizzes are bare minimum. If you're not finishing those, then you're kind of putting yourself up against the wall. So the homework and the quizzes you should be thinking of as bare minimum. That is really the bottom. To be able to do well in a class like this and just do the homework, that's it, and not be doing other stuff like really digging into the worksheets, going over your quizzes several times. You really should be finishing the homework and the quizzes several days ahead of time before the exam, so you can be focusing on just studying the exam. So like I showed you on Tuesday, the prior 2 exams are up there so that you can study from those. So you got to give yourself time though. So you don't want to be doing homework on Wednesday night at midnight when the exam is at 9 in the morning on Thursday. But at any rate, I will remind you, but you want to just be staying on top of the homework, but it is set to be due on the 9th. Any other questions that came up as you were looking through course materials? So make sure you can get into the OneNote on your desktop, not OneNote in the browser. So if you open up that link, it does open in the browser, and if you click the drop-down menu on the top right of the toolbar, it says Open in Desktop App, so you wanted to do that. Anything else that you stumbled across that I didn't talk about? And as you're looking through, it's like reading the syllabus on day 1 is kind of worthless. You really should read it at week 2. Because that's when you sort of know what's happening in the class, you've got some internal questions, and you can sort of look at some of the things. Now, unfortunately, the syllabi that we give you at this college right now, there's so much mumbo jumbo in there that is sort of required from the system office. The more important document really to understand is our schedule, when things are due, when we're going to cover things, when these important due dates are. So I tried to grab everything important out of the syllabus in terms of dates. and they're all right down here. And in terms of grading policies, so the final exam, if it's better than one of your midterm exams, we'll have 3 midterm exams and then the final exam, and if the final's better than your lowest, it will replace that. So it'll count twice. So that's an important thing. And that happens, you know, it's not like something that's obscure. You know, the final is mostly review, so that does help most students. Most of you will have that opportunity to, you know, replace a low exam. Unless none of them are low, that makes my life easier. The better you do, the less grading I have to do. It's so much harder to grade a C paper than an A paper. So just get A's. Keep it simple for me. Okay, so, and again, as you're looking through all the course materials, just ask when you come across something that you're not sure about, and we will figure it out. So the place where we're at today is finding areas. And you learned this in Calc 1, that the area beneath a curve is the definite integral. Right? That's what the definite integral does. It finds the area beneath the curve. Now, we're generalizing that a little bit here. Instead of just having one curve, we're going to say, hey, let's have 2 curves. And so the concept is the same. We are finding the area between those curves, and we're going to use a rectangular partition approximation and then take the limit of it. Now, we're not going to do the nuts and bolts of Riemann sums like you did in Calc 1, where you did a left point, a right endpoint, a midpoint, you know, perhaps Simpson's rule where you use trapezoids. We're going to wave our hands. You did the Calc 1 pre-work stuff where you learned about a Riemann sum. What you need to understand is that when you take the limit of a Riemann sum, you get the exact area. So in your mind, you're thinking about, oh, okay, we're subdividing into rectangles, and if we add up the areas of all those rectangles, we get an approximation. And as you let the rectangles get narrower and narrower, you get a better approximation. And when you take the limit, as the number of rectangles goes to infinity, you will get the exact area. Okay, so that is that's sort of remarkable that you can use it's the integral. It's not on this page yet. It'll be on the next page. So that the integral will give you the exact area. That was a super profound discovery. Before that, you could only find exact areas of things that had nice, you know, straight lines or perhaps some special curves like circles, but finding the area of general shapes is a big deal. So when we're thinking rectangles, well, rectangles area is the height times the width. And when we think about the width, we use this delta x, Greek letter D for difference. So that represents difference in x. That's just the x width of the rectangle. And when we visualize it, we visualize all the rectangles sort of having the same width. Mathematically, you actually can have rectangles that are varying widths, but we don't care, as long as the widths are going to 0. But we generally think of a uniform partition, so all the rectangles have the same width, delta x, and then we let that width go to 0, which means the number of rectangles is going to infinity. So this just represents the height of the rectangle and the width of the rectangle. So there's height and there's width. Does everybody agree that height, f minus g, if you look at a particular rectangle and you pick, the star point is just a random point in the interval, could be the midpoint, doesn't have to be, but f of that star point is up there, g of that star point is right there. When you're finding a vertical distance, you take the upper number and subtract off the lower number. Upper minus lower, and that's going to give you this distance. And if you're at 5 on the y-axis and you're down here at -2 on the y-axis, 5 minus minus 2 gives you that distance. All right, if you're at 5 and at -2, 7 is the difference, upper minus lower. 5 minus 2 is 7. So if you want to find the height of the rectangle, it's always the upper curve minus the lower curve, f minus g. So that's what this is representing, and the magic, the hand-waving piece, that we're not going to go through the whole limit process, is that that's our answer. You get the definite integral. The limit of a Riemann sum is a definite integral. And same thing here, when you're thinking, think about this as the height. Think about that as the width. And when you take the limit of the Riemann sum, you get the definite integral. And so the integral symbol looks like an S for sum, right? It's like a summation. It's summing up the areas of all these little rectangles. So you can think of the integral symbol like a sum. You're summing up all that stuff. So let's take a look at some examples. So our first example, I will always draw a representative, I call it an element, an integration element. You can think of it as a representative rectangle, whatever you want to think about. But we usually are going to draw a line segment that connects the upper curve to the lower curve. Later, we're going to do curves that are on the left and the right, and we'll draw a line across them. So think about that as just a thin little rectangle. It's a representative rectangle, or an element, an integration element. And the thickness of this element, we think of the thickness as dx. That's how wide it is. Again, d like difference in x. So a differential is just the width of that little rectangle. Think of it that way. And then the height of the rectangle is right there, and we're going to do the upper curve minus the lower curve. That'll give us the height at x. And so when we go to find the area here, our area is going to be the integral. Okay, we need to know the x value here and the x value there. We need to know these two x values, right? Because we are going to integrate with respect to the x-axis, so we're integrating on that interval. You know, a and b are these two numbers here. To find those intersection points, we'll have to do a little bit of algebra. So we'll get to that in 1 second. Let's set up our integral first, the inside of it. So the area is going to be the integral of the upper curve minus the lower curve. So here is the upper curve. And then we're going to subtract off the lower curve. And remember, we're subtracting off the entire curve, so we need to have parentheses there. We have to distribute that subtraction symbol. Everybody okay up to that moment? So upper curve minus lower curve. Now we have to come off to the side and do our algebra and figure out these intersection points. Looks like that one's probably x equals 0, but you know, a graph isn't exact, you know, ish. So we have to do math to figure out what those intersection points are. So we're going to set the two curves equal to each other. Right? That's how we figure out where the shared points are. Set the two curves equal to each other. Let's see, I'm going to put a 0 on the left. I'll add the x's over here. So I'm coming up with that. Add the x squared, subtract the 4x. We could divide out of 2 if we want to. You actually don't have to, but you can, right? Divide both sides by 2. Factor out the x. So this tells us then that the two x values where these curves meet are at 0 and 3. So that tells us what our integration interval will be. That tells us that the x value of this intersection point is 0, and the x value of this intersection point is 3. We don't actually have to find the y coordinates of those, do we? Because we're integrating with respect to x, which means we're only looking at the x-axis. So regardless, this point, okay, yeah, we could plug 0 in and see that it's the origin, but we really don't need it. If we don't want to, we don't have to find those y values. All we care about is the x values. How do you get the y values? Plug it into either equation because they're meeting at that point. So if we plug in 0 here for x or 0 here, we will get 0. And if we plug in 3 in either of those equations, we're going to get the same y value. So we get 9 minus 6, so that's 3. But we don't actually need those y values, but just in case we did. Okay, so that tells us then that we're going to integrate from 0 to 3. Those are the limits of integrations. The lower limit is 0, the upper limit is 3. Let's go ahead and keep computing here. We'll have some simplification on the inside of this integral, the integrand. We're going to have negative x squared minus x squared, which is negative 2x squared. And then 4x minus minus 2x, so we get a plus 6x with respect to x. Integrate, we add 1 to the exponent and divide by the new exponent. Shockingly simple. It's remarkable that that actually works. You prove that in Calc 1, that that technique of adding 1 and dividing by the new exponent works. If we plug in 0 here, we don't get anything, right? Plug in 0, you get 0 plus 0, so we can kind of ignore that limit of integration. Everything is going to depend on the 3, so we'll have negative 2/3 multiplied by 3 cubed, which is 27, plus 9 times 3 is also 27, and then subtract out 0. You don't have to write it, though. So we're going to get negative 18 plus 27, so we are going to get 9 square units. Most of our math problems don't have units. If they don't give us units, we don't need to put units. If they do give us units, then we want to put the units. So it all just depends on the context. Any questions when you look at that? Is there any part of the math? Yeah.
Sorry, how did you get the points again? How did you get 0, 0, and 3, 3?
So whenever we want to know where two curves are intersecting, we're going to set them equal to each other. So here is the upper curve right there. There's the lower curve. If we set them equal to each other and then solve for x, that tells us the x coordinates of where they meet.
Oh, and then you plug the x into the equation.
Then we plug the x into the either equation because the curves are meeting at that point. So if you plug the 0 into either equation or the 3 into either equation, you're going to get the same y coordinate. So if you look at that intersection point right there, if we plug this 3 in here, we'll get 3, or if we plug it in there, we'll get 3. Make sense? And then our total area is exactly 9. Which is kind of weird. You look at those two, you look at that shape, that doesn't look like it should be like a whole number of square units, right? It looks like it's probably irrational even, but it's 9 square units. What is the upper curve on the second example here?
The x-axis.
The x-axis, which is y equals 0. So this, we sort of indirectly talked about this on Tuesday when we had those velocity functions that dipped below the x-axis. Remember, if you integrate just straight across a curve that's below the x-axis, you end up with a negative number, right? So if you want to make it positive, you could just multiply by -1, or what we're going to do here, when we look at our representative rectangle here, there's our I usually will put like an x. I didn't do that here, but we're sort of thinking about this at a random x. And then that x is going to slide across the whole region. So if we think of this as a rectangle, and you want the height, you would do 0 minus whatever the negative number is here. So if this is at -4, the height of this rectangle would be 0 minus -4, so we get a 4. Right? So that's how we're going to make the area positive, by subtracting it from 0, which the effect of that is that we're just changing the sign. If we just integrated straight across, we would end up with a negative number. But we're going to integrate 0 minus the curve, which will give us a positive number. So first off, over here we found our x coordinates to be 0 and 3. We have to do the same thing here. We need to find these x values. So how are we going to find those x values?
The lower equals the upper 0?
So we're going to set the lower curve equal to the upper curve. The upper curve here, though, is a curve, right? It's y equals 0. That's still a curve, even though it's not very curvy. But that's still considered a curve. It's a straight line. So we're going to set the curves equal to each other, just like we did before. That's the upper curve, y equals 0. So we're essentially finding x-intercepts. So when you find x-intercepts, this is what you do. You set your function equal to 0 to find x-intercepts. But more conceptually, you're setting the function equal to this curve here, y equals 0. Okay, this is nice because it's already factored. That's how you solve nonlinear equations. Nonlinear equations, you always factor it, so you can set each factor equal to 0 using the 0 product rule. So this tells us because we have a product equal to 0, that tells us that that is 0, or sine of x is 0. This first one, if we add 2 to both sides, we get cosine x equals 2. Does anyone know of an x value that has a cosine value of 2? So whenever you see a basic trig function, like a sine or a cosine, equal to a constant, you should be thinking about the unit circle. How big is the unit circle? Right? It's radius 1. Is there any chance that the cosine or the sine could be equal to 2?
No.
No. Right? If you're on a unit circle, the biggest the x value ever is positive 1. The least the x value is negative 1. The largest the y value is positive 1. The least the y value is negative 1. So could sine or cosine ever be 2?
No.
No. No. So this has no solution right here. That has no solution. So sine of x equal to 0. My recommendation whenever you see a basic trig equation, which again by definition means a trig function equal to a constant. Sine of x equals a third or a half or square root of 3 over 2, whatever, constant. Draw the unit circle. This is the best way to get comfortable with the trig. Whenever you have a basic trig equation, which we are going to have 1,000 of this semester, draw a picture. Pictures, when you're dealing with basic trig equations, help immensely. Is sine the x value or the y value on this unit circle? Y value, right? Sine is y, cosine is x. So draw a picture of where that basic trig equation solutions are. That's where sine is 0.
0.
0 and pi. So that tells us then, now first off, every basic trig equation that has a solution has an infinite number of solutions, right? So if this representative solution is x equals 0, now it's always funny when we use x as an angle, because when we say x equals 0 here, we're talking about the angle x, not the x value in the coordinate plane, right? This is an angle. It'd be easier if they used a theta. Then there's a little less conflict. So when we're here at the angle of 0 radians or 0 degrees, anytime we add 2 pi or 360 degrees or subtract, we get back to that same place and we have a solution. Same thing here over at pi or 180 degrees. Whether you go, so you always have an infinite number of solutions, always, for a trig equation that has a solution. Now for us, when we look at this, based on our graph, we kind of know what the two solutions are. Like if I were to list these solutions, like in a big long list, let's just start way out there and say, oh, well, negative 2 pi is a solution. Negative pi is a solution. 0, right? These solutions are pi units apart. There's kind of a list of all the possible solutions. You can go negative multiples of pi forever, positive multiples of pi forever, right? But when we look at our graph, we are looking for this one and this one, which when we come over here in our list, oh, that's those two. Right? Those are the two that fit our graph. We have certainly one at 0, and then we have the first positive one after 0. There's the first positive one after 0. So those are going to be our solutions, and that is going to inform our integral. So the area will be the integral from 0 over to pi. And now we're doing upper minus lower. The upper curve is 0. So 0 minus the lower curve. And so that is going to be, let's just write it exactly how they have it. We'll deal with integration in a second. There. So upper minus lower. Now we have to sort of manipulate that integrand so that we can integrate it. We can't integrate a product at this point. We'll learn a technique that works for many products, but not yet. So we want to distribute the sine function. So we're going to end up with minus sine cosine. And let's see, distribute that minus, that's going to be plus 2 sine of x. So that is our expanded integrand. One thing that you learned in Calc 1 is that the integral symbol can distribute across sums and differences. So we can write this as two separate integrals, and that's going to be convenient because this first integral is going to be done differently than the second integral. The second integral, oops, I forgot my dx. The second integral is instantaneous. I'll pull the 2 out. You can always factor constants to the front. So that's the distribution of the integral, just like you can distribute a derivative. You can distribute an integral. All right, the second one is instantaneous. Actually, we did sine x, I think, 3 times on Tuesday. The integral of sine is?
Negative cosine.
Yeah, negative cosine. So that's going to be that one. What technique are we going to use for this one?
Substitution.
Yeah, you've only learned one technique other than, instantaneous. So substitution. You have 2 functions here, sine and cosine. You could choose either function. Doesn't matter which one you pick. Does anyone have a preference?
Sine.
Sine? Okay, we'll let u be sine. So if we let u be sine, let's see what happens. Now this is not a reverse chain rule thing like we did the other day. We're not doing a substitution that's linear. That reverse chain rule we did on Tuesday, and we'll do a bunch later, is only when the substitution is linear. That's not a linear function. So if we let u equal sine of x, then du is cosine of x dx. All right, let's see what that gives us. So now we're converting from x's to u's. X is the variable of integration right now, but we're going to switch it to u's. That means we have to switch any x we see, we have to switch it over into a u. So let's go straight across here. Oh, got the minus sign. There's our minus sign. Sine of x, we said that's u. And then cosine of x dx. Cosine of x dx, oh, right there. That is du. So the du is going to drop in right there. Plus, we'll get to that in 1 second. How about limits of integration? So these limits are x limits. If we want u limits, this is our gateway, right? That equation tells us how we exchange x's for u's. This tells us if you put in an x equals 0, you're going to get out a u. Question?
If u is sine of x, would du be negative cosine of x?
The derivative of sine is positive cosine.
Oh yeah.
Make sense? So since the derivative is positive cosine, that minus still is going to sit out in front. So what will u be when x is 0? Sine of 0 is 0. Right? Again, visualize the unit circle. It should be like your third eye. Visualize that unit circle. 0 degrees, 0 radians is over on the right. Sine is second, cosine is first. The second coordinate on the right side of the unit circle is 0. So sine of 0 is 0. So that tells us that our lower limit of integration is 0. Now let's exchange that x for a u. Let's change it into u's. So we take that pi, we put it in right there. Sine of pi is?
0.
0. We love that. The integral from 0 to 0 is how much? 0. Right? There's not a lot of area from 0 to 0. Beautiful. We like 0. 0 is our favorite number. Unless it's our test score. Okay. Integral of sine is negative cosine. So here's where that negative is coming in, because the integral of sine is minus cosine. And that will also go from 0 to pi. So we are at 0 there. And then over here we have plus 2. Let's put some parentheses. Now we have to do upper minus lower evaluated into the antiderivative. So negative cosines are antiderivative. Plug in pi, negative cosine of pi. So again, go to the unit circle. Pi is over here.
Positive 1.
So negative 1. Right? The cosine of pi is negative 1 because we're on the left. The x-coordinate's negative 1. Multiply by a negative, so negative 1 is 1. And then we subtract off what we get when we plug in 0. Oh, it's minus a minus, so that becomes plus cosine of 0. Right side of the unit circle, cosine value is 1. So we get a final answer of 4 square units. So that area is also just a whole number. Surprising. But then you take a circle and the area is not a whole number. All right, any steps there that you're wanting to ask about? Yeah.
What does that difference represent?
So we're talking about this difference right down here.
In both examples, the difference between the two functions?
So the antiderivative of each evaluated and subtracted.
Yes.
So
Area that we are calculating.
yeah, so the way you're thinking about it is that that difference is built in because of the height of the rectangle. And so that difference right there, oh, well, that doesn't answer your question, actually. Your question is this, not there. So there's a difference here, which is just upper minus lower. You're talking about this difference where you plug in the 3 and then you subtract off, plug it in the 0.
My question is more general, like we are calculating this.
Yeah.
I'm kind of looking for an example that, okay, what does it mean? We have two functions and we are calculating the area between the two. What does that represent?
Well, the integral is representing the area between the two curves, and that difference that I think you're referring to is just the evaluation technique of a definite integral. So by definition, when we look at a definite integral, I guess I don't think I have it written up there, but this is the definition. If we have a function and we integrate it from a to b, what you learned in Calc 1 was, oh, if you can find an antiderivative, this is how you take the antiderivative and evaluate it at each endpoint and take the difference. That's the evaluation, so it's a theorem. So conceptually what's happening there will take a little bit of work to look at. But we could do that. I'd have to think about it for a minute because I don't teach Calc 1. That's something that you would do in Calc 1. So capital F is the antiderivative for little f, and then we evaluate it at both endpoints and take the difference. So it's the I guess it's a fundamental theorem of calculus. I forget which one. There's two of them. I guess that's the first fundamental theorem of calculus, I think. So it's the evaluation technique for evaluation technique for a definite integral. Okay, so let's take a look at another one where we're finding area. Oh, more trig functions. It's not going to stop. Get that unit circle, start drawing blank ones, get it down, because the trig functions are going to come like fire hoses. So here it says the region that's bounded between these two curves, and they give us an interval, pi over 4 to 5 pi over 4. So first off, what we've seen, all the ones we've done up to now, we've looked at a graph. They're just not giving us the graph here. So that's going to be the first. It's always easier if you have a graph, so you can sort of see how things are related to each other. So let's go ahead and just look at a graph of these two functions and see what happens. So we know that the sine function, that's the easier one to draw. The sine function, if we look at one period, and these two numbers are between 0 and 2 pi, so one period's more than enough. But it's easier to draw a trig function if you draw the whole period. So let's do that. And then we know that the cosine function starts up, comes down, and then, ooh, terrible. Worse than terrible. Let's see, maybe it's easier for me to draw the cosine by actually putting in my key points first. For cosine, you have your key points form a V. That's going to be a little easier for me to draw the cosine if I put in the 5 key points. So there's our, oh, what? That's actually really nice. Wow. Okay, so there's y equals cosine x, and the red one is y equals sine of x. Okay, now they've given us these two x values, pi fourths and 5 pi fourths, and let's notice on the unit circle, if we look at pi over 4, that's right here, and 5 pi over 4, isn't that down there? 1, 2, 3, 4, 5 pi over 4s. So there's pi over 4, that's 5 pi over 4. If we want to know where these intersection points are, we set our curves equal to each other, right? Aren't sine and cosine identical at pi over 4? Right, pi over 4 is on the line y equals x. 1, 1, 2, 2, 3, 3. Square root of 2 over 2, square root of 2 over 2. Right? Pi over 4, sine and cosine are the same at pi over 4, because you're on that line y equals x. And so if we put the coordinates of the point over here, we would be at root 2 over 2, root 2 over 2. Oh yeah, they're equal there. And how about over here? Isn't this minus root 2 over 2, minus root 2 over 2? Oh, they're equal there too. So these two numbers that they gave us are strategic. They actually have told us indirectly that these are the intersection points right there. That's where sine and cosine are equal between 0 and 2 pi. Pi over 4 and 5 pi over 4. So our area integral is going to be from pi divided by 4 to 5 pi divided by 4. All right, let's draw our representative rectangle, our integration element right there. So that's at a random x. This is the upper curve, this is the lower curve. The thickness of it, dx, the height of it. The height of our representative rectangle is upper minus lower, so it's red curve minus green curve. That'll be the height. So the height is the upper curve, red curve, which is sine. We're going to have sine minus cosine. So there is the height of a rectangle, and then the dx is representing the width. So looking at that, is there any part that you're not sure about?
Sorry, could you please go over how we determine which one is the upper, because they go up and down?
Yes. So so this is a good question. When you're in your region, and I drew them in with different colors, so it should be clear that no matter, when you draw your representative rectangle, you can draw it anywhere in your region. And mentally, you should be actually envisioning, oh, we have, an infinite number of rectangles that we're sort of adding the areas up. And when you look, no matter where you draw this vertical element, this representative rectangle, you could draw it here, if I can draw, there, right? Anywhere in this region, the red is always on top. So if this interval came over to here, where you had a piece where the red was on top, but then another piece where the green was on top, we'd have to break it apart so that we could do red minus green and then add green minus red.
And we need the graph to know which one is top, or there is a...
Yes, you could plug in points and check. You could pick test values. So you could pick a test value in between, so you could analytically do it. It's easier with a graph. It's easier with the graph. We can see that this red curve is going to be the upper curve all the way through the interval. How about our antiderivative? What's the antiderivative for sine? Negative cosine minus antiderivative for cosine, sine. So there is our total antiderivative and our limits of integration, pi divided by 4 up to 5 pi divided by 4. Now, it's very convenient that we already have the unit circle up here, because now we have to evaluate sine and cosine at those two angles, and we can see when we plug in 5 pi over 4 for this antiderivative, cosine of 5 pi over 4 is right there. So we have a negative and then negative root 2 over 2. And then we have a negative, and then sine of 5 pi over 4 is also negative. So that is the antiderivative evaluated at the upper endpoint, upper limit of integration. And now we do the fundamental theorem thing where we subtract off the antiderivative. I'm going to put it in parentheses because it's a multi-termed expression. So subtract off the antiderivative at the lower limit of integration. So we have minus cosine of pi over 4 is root 2 over 2. And then we have minus sine of sine of pi over 4, which is root 2 over 2. So that's what we end up with. A bunch of root 2 over 2's. This is positive root 2 over 2. This is now positive root 2 over 2. When the minus is distributed, you have root 2 over 2 and positive root 2 over 2. So you have 4 of them. So 4 root 2 over 2's. So if you added them all up, you'd get 2 root 2. That will be our area. So nice that we have colors. Man, when it was just chalkboards and white dusty chalk, so much harder to distinguish. Colors help. Okay, so I want to look at this one. This is another function that's going to show up a bazillion times this semester. Of x to the 2/3. And the important thing here, when you look at that exponent, it's a fractional exponent. And the graph of x raised to a fractional exponent is going to look the same, essentially, no matter what that fractional exponent is. 2/3, 4/5, 9/11, 1/2, whatever. If it's a fractional exponent, you are going to get a bird wing. Now, depending on what your interval is, 99% of the time we only care about the right of the y-axis, and it's going to look something like that. Square root of x, right? That's what you think of when you see square root of x. Square root of x is x to the 1/2 power, fractional exponent. All of them are going to look like that. Now, yes, sometimes you're going to get stuff on the left, and we can talk about when you have something on the left and when you don't. All depends on what the denominator is. Right? When the denominator is even, it's a root, like a square root when there's no solution, right? If it's an even root, you have no solution. Odd roots, like a third root, you will have stuff on the left. But most of the time we are not looking to the left. But if we are, we can look more carefully at it. And go to your calculator and graph a bunch of these. But this is the main idea is when you have a fractional exponent on x, quadrant 1's a bird wing. It's always going to sort of look like that. Also looks kind of like, well, it looks like a square root function. That's the best thing to think of it as. So you look at a representative fractional exponent, square root. They're all going to look about the same. And then it says we have y equals 4. Y equals 4 is on the y-axis, and that's going to be a horizontal line, and it's going to meet the graph right there. Now it says the region in the first quadrant bounded by these two curves. Bounded means those are the boundaries. And we're in quadrant 1, so there's this other boundary. Well, let's see what color I'm going to use shading. So the other boundary is going to be the y-axis itself. So because it says that we're in quadrant 1, so that is the region that is bounded. So when a region is bounded, that means it's not going off to infinity. You can draw a circle around the region. So it's contained. All right. Now, let's draw our representative rectangle. So representative rectangle, I'm going to imagine that at a random x. And then we need to know the limits of integration. So we need to know the x value here and the x value there. So we're going to integrate across. Wherever you draw your rectangle could be anywhere within this region, right? So there are rectangles that go from 0 over to here. And then the idea is that each of those rectangles has an area, and we're going to accumulate all the area from each of those individual rectangles. All right, so we need to know that point. So once again, we set our curves equal to each other. So we set x to the 2/3 equal to 4. We just want to solve that for x. That will tell us where they meet. Well, if you raise both sides to the 3/2 power, you get that, right? 2/3 to the 3/2, you get 6/6, which is a power of 1. When you have a power to a power, you're multiplying the exponents. So if we raise this to the 3/2 and we raise that to the 3/2, multiply, you get 6/6, so that's x to the 1. And then we have on the right 4 to the 3/2. And there's two ways to evaluate that fractional exponent. You can trigger the denominator first, or you can trigger the numerator first. It doesn't matter. So the numerator is a power, the denominator is a root. If that root creates a perfect root, that's the fastest way to go because you're shrinking the number first. So the square root of 4 is 2, so we shrunk it down to 2, and then we have to cube it and we get 8. Or you could do 4 cubed first. 4 cubed is 4 times 4, which is 16 times 4, which is 64, and then do the square root of 64, which is not too hard in this case. Usually it's going to be a lot quicker if you can do the root first, though. All right, so that tells us that this point over here is 8 comma something, again, we don't care what the y value is, but we know that that y value is 4, right? We know that because this function is y equals 4. Doesn't really matter in our, because we're integrating with respect to x's. Okay, so that tells us that the area is going to be the integral from 0 over to 8. All right, upper curve. Which one's the upper curve?
Y equals 4.
Y equals 4. It's the red curve. So upper curve, so if you zoom in on this one rectangle right there, our representative rectangle, the height of that rectangle is going to be the top curve minus the bottom curve, upper minus lower. So upper curve is 4, lower curve is x to the 2/3. So that will represent our area. Exactly. Not an approximation. So integral of x to the 2/3, just like a polynomial, add 1 to the exponent, divide by the new exponent. So we're going to add 3 over 3. So we're adding 1. So we're going to get x to the 5/3 divided by 5/3, which will turn into a multiplication of 3/5. That. Once again, plugging in 0, non-contributor, because both of these have an x, so you plug in 0, both of those will become 0. So we really are focused on that 8. We'll get 32 minus, all right, let's see if we can do it. So 3/5 is the denominator, reciprocal of the denominator, right? Divided by a fraction multiplied by the reciprocal. So now we're plugging 8 in here. The denominator is the root, that's the cubed root. The numerator of that fraction is a 5, so that's the power. So the cubed root of 8, 2, and then 2 to the 5th, 32. So that. Now, obviously, you could multiply the 3 and the 32, right? But the way that I see that's going to work a little bit faster in our favor is that we have a common factor of 32. So isn't that common factor, can't, if we wanted to, just factor it to the front? And then what would be left when we factor a 32 out of there? So we're going to be left with 1 minus 3/5, which we can do in our head really easily. That's 5/5 minus 3/5, which is 2/5. So we're going to have 32 times 2/5, and we will get 64 over 5. Any part of that you want to ask about? Anything that... I wonder if there's trig on the next slide. Sebastian, you ready to go? Is that a confident yes?
Kind of.
Or are you telling me what I want to hear? All right. Let's look. Now that we have those vertical rectangles dialed, let's switch it up. Let's go horizontal. So the regions that we have looked at so far, we had a distinct upper curve and a distinct lower curve. And we could always draw a vertical line that connected the two. These regions here, we cannot draw a vertical line and have a distinct upper curve and a distinct lower curve. Right? If we draw this vertical line right there, oh, it's red on red, not good. You know, here we have whatever this constant d value is on the top and then the red on the bottom. So it's inconsistent. It's not definitive. There's not a definitive upper and a definitive lower. So we can't use a vertical rectangle. We're going to use a horizontal rectangle here, a sleeping rectangle. So our representative rectangles are going to go sideways here. So for all of these, we do have a distinct left curve and a distinct right curve. And I'll say that this random horizontal rectangle, this random integration element, is going to be horizontal at just a random y value. So the vertical rectangles are at a random x, the horizontal rectangles are at a random y. And that y changes between C and D, just like our vertical ones moved between A and B. So same idea. So now we're envisioning integrating on the y-axis, so from C up to D, C up to D, C up to D, so we have to find C and D. How about the height of our sleeping rectangle? What is the height? Which maybe we want to say its width. The thickness of the rectangle will be dy instead of dx. So we'll have a dy as the thickness of the rectangle, which we sort of think of as the width of the rectangle, even though it's sleeping. So the height of the rectangle is sideways. How do we find the height of a horizontal segment? What do you think? Yeah, exactly. If this is 6 and this is 1, what's the difference between the two? 5. Right? How do you get the 5? We know that this distance in here is 5. We did right minus left. So if you're vertical, you're doing upper minus lower. If we're horizontal, right minus left. That's how you find a horizontal distance, right minus left. Vertical distance, upper minus lower. Horizontal distance, right minus left. So that's what we're going to do. And that's what they've shown us with this theorem here, or with this definition. There's always kind of a conflict between theorems and definitions. So this definition, we're going to take the right curve, subtract off the left curve. Right minus left. That'll be the height of the rectangle. So we're thinking of this piece right in here as height, and we're thinking of that as the width of the rectangle. Even though it's this direction, we're saying that's the height and that's the width. So it's parallel in concept to the other one we did, the vertical ones. All right, so there are two. Let's set up the first one and then we'll take our break, because this is probably going to, give us some questions. The first thing I want you to notice is that we've got this absolute value function, and that function is symmetric about the x-axis. This parabola is also symmetric about the x-axis, right? Negative y squared, and then it's just shifted 2. It's like y equals x squared is symmetric about the y-axis. Y equals negative x squared is symmetric about the y-axis. And then if you shifted it, it's still symmetric about the y-axis. This one's just the other direction. Y squared is symmetric about the x-axis. Negative y squared is also symmetric about the x-axis. And then if you shift it, it's still symmetric about the x-axis. The point being, this region right here has the same exact area as the region right below it. So we can use a symmetry thing here, which will make it a little bit faster. So we know that the total area is going to be the area of this upper region times 2. All right, so now let's draw our sleeping rectangle. So our sleeping rectangle is going to go across like that. This is at a random y value. And then we're going to imagine all these y values between 0 and whatever that number is. Well, that'll give us that area there. So let's set up our integral and then we'll take our break. So the total area is going to be 2 multiplied by, so this is a symmetry. This 2 is by, This 2 is by symmetry. And our limits of integration, let's find them in 1 second. So right curve, what is the right curve? 2 minus y squared, right? That's the curve on the right, so 2 minus y squared. That's the right curve. Minus, come on, the left curve. What is the left curve? Yes and no. Remember, the absolute value is a piecewise defined function. So these two pieces are different, right? Depends on where you are with respect to y. If you're up here, isn't that curve up here y? Well, I should start with the x since that's what they did. Isn't the curve up here x equals y? And then what's the curve down here? X, yeah, x equals negative y. Okay, so that's going to tell us that if we're going to focus in on this upper region here, the left curve is x equals y. And so we're going to get a minus y dy. Hey, we haven't had one black screen, have we? Oh, I wonder if they did fix it. Okay, great. How about limits of integration? How do we find limits of integration? We set the functions equal to each other. So the left function is y. The right function is 2 minus y squared. That's a nonlinear equation. Whenever you have a nonlinear equation, the best thing to do, everything to one side and factor. Linear, letters left, numbers right. Nonlinear, everything to one side and factor. So this is going to give us y squared plus y minus 2. So this will factor into y plus 2 and y minus 1. So y will equal 1 or negative 2. What do you think that y value is, 1 or negative 2? 1, right? That's definitely not negative 2 above the x-axis. So we are integrating from 0 up to 1. Now, before we take our break, we'll do the integration afterwards. What do you think that negative 2 represents? What does y equals negative 2? How do you see it?
If the y keeps, or if the graph were to keep going, it'd be the lower bottom left intersection.
So if this line keeps going, right, because y equals x does keep going, it's not relevant for the problem because we're stopping at 0, but if you did extend this function, if it did keep on trucking this way, that's where it's going to hit that curve at y equals negative 2. What do you think this y value is? Negative 1, because that's got to be symmetric. So if we went up 1 to get to that one, we're going to go down 1 to get to that. So that's what that negative 2 is representing, the unseen intercept. All right, let's go ahead and take our 10-minute break, and we will resume in 10 minutes. Let's see. Will it work? Okay, so now that, yeah, sure.
What the shoes were
Oh,
again?
that came. Okay, so, oh, it worked. Okay, so the integration is not too hard here. Whenever we see a polynomial, we kind of breathe a sigh of relief because we just have to add 1 to the exponent and keep going. So let's see. Do that. Let's go there. That. So we will end up with 2 multiplied by, integral of 2 is 2y, and then y cubed divided by 3, and then y squared divided by 2. And that will all go from 0 to 1. And once again, the 0 is not going to contribute any area, and we just have to plug in that upper limit of integration. We'll get 2 minus the third minus a half. And when we do all the math there, we end up with, what was that answer we ended up with? 14 over 6? Simplify, so 7 over 6. Yeah, if we do the reduction. So double check that you can get 7 over 6. That will be the total area. So we took half the area and then doubled it using that symmetry. All right, I think you're ready to try one. So let's try this. You all try this one. I'll just draw the representative rectangle across. That's at a random y value. And let me just make sure it's clear. What curve is on the right? Is it the one, is it this curve, or is it the one that's negative 2y squared? Which one is the one on the right?
Negative 2y squared.
So the negative 2y squared one, that's on the right.
This should be 14.6.
No, wouldn't it be 2 times
Because
that?
there's 2 terms. That's
The top half.
That's just the top.
Oh, okay, so this math is not right here? But doesn't 14 over 6 reduce to this?
It'd be 7 over 3,
Because
right?
it's 7/6 is the top half.
Got you, so it's 2 times 7 over 6?
Yes.
So then it's gonna be 7/3. Thank you. Thank you. Doing the math. Okay, so the right curve is this one. This one is the one that's on the right. All right, so go ahead and see if you can find this area. Or at least set it up. Set up. There's a lot of arithmetic here, so at least get set up first, and we'll double check that you've got it set up right before you start doing the integration. Oh, yeah, while you're doing that, I should try to learn names. Fatima. Arnulfo. Nikesh. Nolan. Shaq. Jordan. Danny. Chewy. Brianna. Brianna or Brianna? Brianna. Evan. Lauren. Che. Yesenia. Trevin. Trevin, were you here Tuesday? Oh, okay. That's Gilbert. Kishore. Brian. Ravel. Peyton. Delilah. Ah, I did it again. Next time. Let's see, Ben. Alvaro. Jose. Ishmael. Reza. Laura. Sebastian.
Here.
And Erica.
Here.
All right, so let's see if you all did right minus left properly. Sounds simple, right minus left. So the area will be the right curve minus the left curve. So we're gonna have a minus sign that's gonna have to distribute, so I'll write the left curve in parentheses just to make sure that no funny business happens. All right, limits of integration. So limits of integration, we're gonna set the two functions equal to each other. And let's see, I think that's what I'm getting to simplify there. Is that what you all ended up with for your integrand? Minus 3y squared minus 3y plus 18. And then when we set the curves equal to each other, y squared minus 3y plus 12. Clearly non-linear. Non-linear equation you want to solve, shove everything to one side and factor. That's our strategy. So I'm going to move everything to one side. We'll get 3y squared plus 3y minus 18 is 0. I'm going to divide out the 3 just because it cleans it up and makes the factoring look a little easier. Whether that's true or not, who knows? So we're going to have y plus 3, y minus 2. So what are the 2 y values? Yeah, 2 and negative 3. So negative 3 is going to be the lower right here. And so in this case, we don't really care what the x value is, because we're integrating with respect to y. So these 2 points, this one, again, I don't know what the x value is, but the y value is 2. But you know how to find those x values if you were asked to. You plug them into either function and get the x value. So we're going to integrate from negative 3 to 2. And once again, we have a pretty nice integrand. We can just use our power rule here. So we're adding 1 to the exponent and dividing by the new exponent. And then we'll evaluate that on the interval negative 3 to 2. And I'll let you type in that stuff, get that, plug in the 2, plug in the negative 3, and take the difference. When class ends, I'll do the arithmetic there and put it there just so you can confirm that you got the right answer. But that's the setup. Any part of that you're curious about? Dalila? No questions? I said it right. Sebastian?
So when you're doing this kind of problem, you could choose either the top or the bottom part to be able to so no matter if you choose the top part of the x-axis or the bottom part of the x-axis, it will still give you the same result.
With this one, we don't have any choice because this is not symmetric in any way.
Mm-hmm.
This one, we could pick the bottom half and double it or the top half and double it because we have symmetry about the x-axis.
Oh, okay.
But this one, we don't have symmetry about the x-axis, so we have to integrate through the whole green region.
Right.
Here we integrated just through the top of the green region and then doubled it. Here we have to go through the whole thing because there's no symmetry. We have no choice there.
Follow-up question.
Yeah.
So for the first one, how much time could it save if you duplicate it? Then
A few minutes.
okay.
I mean, the other integral that you're going to get is going to look pretty similar. What is the left curve here is negative y, so you would do 2 minus y squared minus y, and it's going to look a lot like this, actually. So you're basically going to be doing this same amount of work twice, and then adding them together. Yeah, so, but it'll save a few minutes for sure. Definitely save a little bit. Now here's one that is simple in both directions. So if you have a region that's vertically simple, I think of it as vertically simple if I'm using a vertical integration element, a vertical rectangle. And I think of it as horizontally simple if I'm drawing sleeping rectangles. You can do either here, right? If you draw the representative rectangle vertically at a random x, that works, right? Because no matter where you draw it, red's on top and the black curve's down below, all the way through. So you can think of it as vertically simple. Similarly, if you drew a horizontal integration element like that, that would also work. Because no matter where you drew that green sleeping rectangle, black curve's always on the right, red curve's always on the left. So it's not going to matter at all which way you go. Well, let's do it the harder way, because that's the way that we don't want to do it. We want to do it vertically. Vertically just makes more sense, because you see the rectangles, you've done it in Calc 1 a million times, you can see them going across. The sleeping rectangles are a lot harder. So that's why we're going to do them. Now, when we do the sleeping rectangles here, we do the horizontal rectangles, that horizontal rectangle is at a random y, and we're imagining all these green rectangles stacked on top of each other, and we're adding them all up. Now, with the horizontal rectangle, we are doing right curve minus left curve. When we have a right curve, what is the dependent variable? What is the dependent variable when we have a right curve? And a left curve, when we do horizontal, sleeping rectangle.
Why?
The dependent variable is x. So, right, if you look at these two, we have to isolate x. When we're looking at regular functions, they're functions of x, so we isolate y. Y equals x squared, y equals negative x squared, y equals negative x squared plus 2, whatever. If we're dealing with vertical rectangles, we use y as the dependent variable. In other words, we isolate y equals something. When we go horizontal, x is the dependent variable. It depends on y, so we have to isolate x, and then we're going to have y limits of integration. So when we look at this one, there's a little bit of shenanigans going on, because this right curve, what is the equation of this right curve? We have to isolate the x. I can hear you thinking. So x is?
Cube root of y.
Cubed root of y, thank you. So that's the right curve, x equals cubed root of y. And then how about the left curve? X equals, say that again?
X equals y squared.
Y squared, right? If we want to isolate x here, we're going to square both sides, so we're going to end up with y squared. So that's the big basic concept to remember. Vertical rectangle, you isolate y. Horizontal rectangle, you isolate x. When you're doing right minus left, aren't those x's that you're subtracting? If you have a horizontal distance, if that's x equals 7 and that's x equals 2, right, you're subtracting x's. So you want to write these as x values. You want to isolate x. So then when we go to set up our integral, we are going to have that the area is equal to right minus left dy, and then the limits of integration are going to be on the y-axis here. The limits of integration are going to go between the two intersection points right there. How do we find those two intersection points? Set them equal to each other. So we're looking at y squared equals the cubed root of y. We want to know where those are equal. So the simplest way, fractional exponents stink. So let's get rid of the fractional exponent. What can we raise both sides to get rid of the fractional exponent?
Square.
3.
Oh.
If we square this, we'll end up with a 2/3, which is still a fractional exponent. But if we raise both sides to the 3rd power, so we're going to raise both sides to the to the power of 3. We're going to cube both sides, raise both sides to the 3rd power. When you have power to power, you multiply, so you get y to the 6th. Here you get 1. A third times 3 is 1. Now, this is a pretty easy solve. Nonlinear, everything to one side and factor. So everything to one side and factor out of y. We get that. So what are our two solutions?
0 and 1.
0 and 1, right? Y equals 0. Y to the 5th minus 1 equals 0 means y to the 5th is equal to 1, and the 5th root of 1 is 1. So we have our two solutions, 0 and 1. Those become our lower and upper limits of integration. And then we can, bless you, integrate. We add 1 to the exponent, so we get 4/3. Dividing by 4/3 means multiplying by 3/4. And then minus y cubed over 3, 0 to 1. We've seen this all day. lower, having a limit of integration of 0 is often really nice. Often evaluates to 0. So this all boils down to 3 over 4 minus 1 over 3. Common denominator is 12. So multiply that one by 3, we get 9. Multiply that one by 4. So we're going to get 5 twelfths. Then on your own, you could do it the other way just to confirm that you get the exact same answer with vertical rectangles. A little bit easier that way. Much more intuitive. We're just so used to function meaning function of x. We don't usually emphasize like we should. Function always depends on the independent variable. Is it a function of x? Is it a function of y? Like these, when we go horizontal, these are still functions, but they're functions of y instead of functions of x. Functions. Oh, trig. More trig. So this time, let's go ahead and graph this because graphing is important. One thing that is going to be, you're going to notice when you take Calc 3 next semester, Calc 3 is very, very visual. In Calc 3, you frequently have to graph in order to get your limits of integration. Many times in Calc 2, you don't really need to graph to get your limits of integration. Often you could kind of reason them out, but it's very helpful to get this graphing thing down here because in Calc 3, frequently you can't reason out your limits of integration. You have to graph in order to find the limits of integration. So I really will try to emphasize the graphing component of this because it's so important when you get into Calc 3 to be able to graph these things and find zeros of trig functions quickly. So let's go ahead and take a peek at this. The first function is the sine function, which we've looked at already. That's the easier of the two basic trig functions to graph. We'll graph one full period. I'm going to regraph that so that the amplitude looks a little more even. All right, so there's sine on one period. That's more than enough. 0 to pi is within 0 to 2 pi. So 0 to pi is just going to be to that midpoint right there. Okay, what is the other graph? What kind of function is it? Say again? Nope. There's no trig function in there, right? Because there's just x's, there's not a trig function, so it's not, that one's not going to be a trig function. It's going to be a parabola, right? If you wrote this out, this is going to be y equals x squared minus pi x. So that is a parabola. Is it opening up or down? Up, because the leading coefficient is positive. Now, can you tell me what the zeros of this parabola are?
0.
0 and pi, because this is factored here, so when we look right there, x equals 0 or x equals pi will cause that expression to be 0. So when we come to graph it, there's 0 right there, and there's pi. This one's over here at 2 pi. That's not even in our interval, so we don't really have to worry about it. So 0 and pi, and you said it opens up. What would be the first coordinate of the vertex? Pi over 2. Right? The vertex has to be, if it's a parabola, the vertex has to be dead center of the two zeros. Agreed? If it's a parabola and you know the two x-intercepts, the vertex has to be in the middle. So we don't know what the y-coordinate of the vertex is, and we don't care. We're just trying to get relative position. So we know that the parabola is going to be the lower curve, because it's a parabola that's opening up with those two x-intercepts. So that means it has to be down here. The vertex has to be below the x-axis. And we know that the x-coordinate of the vertex is going to be at pi over 2, but we don't need it. That's just sort of beside the point. So this tells us if we're drawing vertical integration elements, vertical rectangles, at a random x value, that's our picture. So now we see clearly that the sine curve is the top curve, the upper curve, and the parabola is the lower curve. So this is going to be y equals x squared minus pi times x. Is that good with everybody? So that tells us then that the area will be the integral from 0 to pi. Now, if we wanted, could we use symmetry here? So if we drew this vertical line at pi over 2, wouldn't the area to the left of pi over 2 and to the right of pi over 2 be the same? So we could go integral 0 to pi over 2 and then double it. We could, if we were contrarians, integrate from pi over 2 to pi and double it. But who the heck wants no 0 in a limit of integration? Well, the contrarians. So we definitely want to keep the 0 limit of integration. So we can either go 0 to pi or 0 to pi over 2 and double. We also hate fractions, so why go to pi over 2 when we can go to pi? Plugging in pi over 2 or plugging in pi doesn't matter. So this symmetry is not going to save us time like the other problem did earlier. Okay, so upper curve we said is the trig function minus the lower curve, which is the parabola. Again, remember that this minus sign has to be distributed, so I'll put minus in the lower curve in parentheses just to make sure we don't lose a sign. And then this will be integral 0 to pi of sine minus x squared plus pi multiplied by x. So there's our simplified integrand. Integral of sine? Negative cosine. Man, we've done that like 6 times now. Minus x cubed over 3 plus pi x squared over 2, 0 to pi. Finally, we have one where 0 actually contributes to area. All right, so let's do this carefully. Maybe I'll put everything in big parentheses this time just to emphasize that fundamental theorem of calculus thing. So it's going to be the antiderivative, which is this whole thing evaluated at pi, goes there. This whole antiderivative evaluated at 0 goes there. Then we subtract the 2. So plugging in pi, cosine of pi, negative 1. We're on the left side of the unit circle. X value is negative 1. Multiplied by a minus makes positive 1. And then here, nothing we can do. Just going to look nice and irrational. And ooh, another pi cubed. We have that. Now we're going to plug in the lower limit of integration. Cosine of 0 is 1, so we get negative 1. Oh, that's 0. Oh, and that's 0. So we get some 0, but not all 0. So this becomes 2, 1 plus 1. These guys, we can get a common denominator of 6. Everyone okay with that? So we're going to have, this one's going to get multiplied by common denominator of 6. That one gets multiplied by 2, so we're going to have negative 2 pi cubed. That one gets multiplied by 3, we have 3 pi cubed. So 3 pi cubed minus 2 pi cubed is 1 pi cubed. So we're going to have 2 plus 1 pi cubed over 6. There is our answer. Can I grab that square? Move it. In. Okay.
Why does the second, like the 2 pi, why does that get cubed?
Right here?
Yeah.
So that's getting cubed because we are, so the cube is coming from here, pi squared times pi. So when we plug in the pi here, we get pi cubed over 3. When we plug in the pi here, we get pi squared times pi, which is pi cubed over 2.
Okay,
That part makes sense?
yeah.
And then we're doing the common denominator thing, multiplying this one by 2 over 2, multiplying this one by 3 over 3, to get a common denominator of 6. All right. 2 dimensions. Goodbye. Our dabbling in 3 dimensions is going to be in situations that are very symmetric and very user-friendly. 3 dimensions in Calc 3 will be like getting lashes. 3 dimensions in Calc 2 is going to be just a friendly little dabble where we're using lots of symmetry. But we can do we can solve some amazing problems in 3 dimensions with Calc 2 when there is a lot of symmetry. So, we look at that weird solid object up there. And our goal, when you're in Calc 3, the goal is volume. Right? When you're in 3-dimensional space, the goal is volume. You want to find the volume of a solid object. Calc 2, we're finding areas of 2-dimensional regions. Calc 3, you're finding volumes of 3-dimensional regions. So here's how we can solve for volume in Calc 2. We're thinking we're gonna do a Riemann sum, but we're gonna wave our hand. You're not gonna have to pick any left endpoint, right endpoint, none of that business. You now know that the limit of a Riemann sum is a definite integral. That's your Calc 1 takeaway. Limit of a Riemann sum is a definite integral. So we've got this region, lots of symmetry. You've got a cross section which creates an area, creates that parabolic looking area. So that's called a cross section. And if we think about what we just did on the last slides, you either integrated with respect to y, where you had all those sleeping rectangles, or you integrated with respect to x, you had all those standing rectangles, and you found area. The idea is very similar. Instead of a height that's going to move through a region, we have an area that's going to move through a region, except our region is now 3-dimensional. So you can imagine that parabolic looking thing. Any place where you take and create a cross section, you're going to have a similar looking shape. It's going to have a different area though. Just like our rectangle, as it slid through our region, had different heights. Here we're just upping 1 dimension, and instead of height varying as you move through your region, area is going to vary as you move through the region. So the idea is, can we find a function for the area that measures it at different x values? That's going to be our goal. Now, cross section is paper thin. There's no volume for a cross section. Cross section has no thickness. Cross section is paper thin. When we want to inflate it so that we have a little bit of volume, a mini volume, a very thin volume, we call that a slice. So difference between cross section and slice. Cross section is 2-dimensional. A slice is that 2-dimensional cross section with a little bit of thickness to it. So it creates a very narrow volume. So it's like a slice of bread. And then we're going to have a bunch of slices of bread stacked together, and we want to find the volume of that loaf. It's kind of the idea. So what we're doing then, instead of picking a point to create a height of a rectangle, we're picking a point to find the area of a cross section. So this right here is the cross-sectional area at that x sub k star. So then there's going to be a bunch of well, you can see it right here. So as the number of slices as the slice of bread gets narrower and narrower, there's more and more slices. But if you add them all up, you're approximating the volume. But then we do the magic, the Calc 1 magic. You take the limit of your Riemann sum and you get a definite integral. So up here, the A is the area of a slice multiplied by I said a slice. Area of a cross section multiplied by the thickness. So this is a slice, If you take the area and you multiply it by the thickness, that's going to give you the slice. You're going to get volume for that slice. You add up the volume of all the slices, you get an approximation for the area, or excuse me, approximation for the volume. So this is a slice, it's a little volume. You add them all up, you get the total volume. And then as the slices get thinner and thinner, you're letting n go to infinity so that you have an infinite number of slices, then you get the exact volume. The integral is going to be the limit of that Riemann sum. So let's do it. Sounds a little complicated, but it's actually not as complicated as it seems. So I say. So there's also another conceptual way you can look at this. When you think about integrating what we just did a minute ago, we were integrating, if you imagine the rectangle scenario, that's kind of what we were thinking of doing, right? We found the height, whether it was vertical or horizontal, multiplied it by dx or maybe dy if it was horizontal. Here you're integrating height, and height really is just a distance function, right? You're finding the distance between two curves. If you integrate distance, we got area. When you integrate area, you get volume. So there's going to be this little bootstrapping thing where if you integrate a distance function, you get area. If you integrate an area function, you get volume. All right? So that kind of thing is going to be where we're going. So you can think of the integral in different ways. You can think of integrating height or distance to get area, or you can look at this integral and say, oh wait, that is a rectangle, so this is an area, and this summation sign, this integral sign is adding up a bunch of little areas to get a total area. So you can think of it in two ways. You're adding a bunch of little areas to get a total area, or the integral of distance is area. And then the integral of area is volume. So you can think of this as two ways. You can say, oh, if I integrate area, I jump up one dimension to 3 dimensions and get volume. Just like here, we integrated a one-dimensional quantity and we end up with a two-dimensional quantity, area. Or you could come in here and say, oh, the area multiplied by dx, that gives us a thin volume. And if we add up all the thin volumes, we'll get a total volume. So two ways to think about it, depending on you know, like the math people love to think of this conceptual thing. Oh, if we integrate distance, we get area, and if you integrate area, you get volume. Physics people tend to want to know, well, what is this physical quantity in here representing, including the differential? This physical quantity is representing area, and the integration symbol adds them all up. This physical quantity is representing a small volume, and the integration symbol adds them all up. So you can do it either way. So let's look at that solid object. We've got this solid object with base in the first quadrant. So I've taken the first quadrant, which is down in the xy plane. In 3 dimensions, the xy plane's in the bottom and z goes up, the 3rd dimension. So I took that xy plane and I rotated it up into here so that we can look at it. You know, there's the x-axis, and the y-axis is there. So it says that we have the quadratic curve root, not quadratic. We have the curve y equals square root curve of 3 minus x, that's this one. And the line x equals 2, which is vertical, and we're in quadrant 1. So if we've got that square root curve and this vertical line, we're in quadrant 1, so we naturally have the two axes also, x-axis and y-axis. So the region that we're looking at over here, this square, this is called a cross-section, not a slice. It's not a slice until we add some thickness to it. So that cross-section, you see that red line right there? That's the same as that red line. So this square is coming right out of the board. Okay, so the red line is indicating where the square is. So they're telling us that the cross-sectional shape are squares. So they're saying that these are So we've got this solid object. Every single cross section is a square. And they're telling us that those squares are perpendicular to the x-axis. So if I had this base region right down here in the xy plane, this weird trapezoidal looking thing, and you said that we're going to stack a bunch of squares, you could stack your squares perpendicular to x or perpendicular to y. So they have to tell us. It's not enough to take that base region in the xy plane and say, oh, the cross sections are squares. Well, we need to know what direction. Are the squares going perpendicular to x or perpendicular to y? So they tell us perpendicular to x. So this edge right here of the square I've drawn perpendicular to the x-axis. And that's what they've shown here. It's perpendicular to the x-axis. Okay, so if we were to take that square and pull it out, it's going to look like that. So that square is right there, that square is right there. That's our representative square. What is the area of a square?
X squared.
Yeah, base times height, x squared, depends if the side is x. So the function is y equals root 3 minus x. So that's this distance, right? So this distance right there is root 3 minus x. So what does this distance have to be? Root 3 minus x. Okay, so the side length of this square, the side length is root 3 minus x. So the area of this square is the square root of 3 minus x squared, which is 3 minus x. So that tells us the area of the square as a function of x. When we look in here, let's actually look up here. When we're at x equals 0, the side length is going to be maximal right there. That's going to be the square with the biggest side length. And it's going to be up to, if you plug in 0 right there, this distance is square root of 3. So the square right at 0, which is going to be this back square right there, that's where x is 0. That back square is going to have how much area? If its side length is root 3, 3. That means it's going to be root 3 times root 3. So the area would be 3. So come over here, plug in 0, and we get 3. So it checks. If we are at, let's pick the other extremity. What about if we're over here at 2? So 2 is this square right there. Ooh, that's going to be kind of hard to draw, but you can kind of see it there. It's that square. What is the side length of the square when x is 2? 1. Right, if you come to 2, plug it in there. The height there is 1. So the side length is 1. So what should its area be? 1. Come over here, plug in that 2 right here, and we get 1. So this area function is going to build the area for all the squares for all the x's that you choose between 0 and 2. So that's the area function. That's what we were looking for. So our theorem says integrate area and get volume. So if we can find an area function that's continuous throughout the region, the solid, then all we have to do is integrate area and we have volume. So volume is going to be the integral of area. Well, that area function is as simple as it gets. It's linear. And what are our limits of integration? When you look up here, 0 to 2, right? We have squares stacked next to each other for all those x values between 0 up to 2. So those are our limits of integration. So that is what we're looking at. That is the volume of that solid object. Find our cross-sectional area and integrate it. All right, so this part is simple. So tell me where you have a question or you want some clarification. Plugging in 0 gives nothing again. 6 minus 4 is 2. A whole number for the volume of that thing, really. So is there a piece of that that you want clarification on? So here we are constructing our solid object. They're telling us, here's your base. Put squares perpendicular to x. They could say, put triangles perpendicular to x. They could say, put semicircles perpendicular to x. They could say, put any geometric object they want perpendicular to x or perpendicular to y. Let's try another one. These take a minute to sort of digest.
So wouldn't it be 1/2 x squared?
1/2 x squared for the area of a square?
No, so the 3 minus x. Would
Oh,
So the answer is 4, not 2.
yeah, I was in the middle of saying that, oh, this is the easy part, and that's where I made my mistake. So integrate 3 to get 3x, integrate x to get x squared over 2. Plug in 0, get nothing. We get 6 minus 2, so that should be 4. Thank you.
Yeah.
Thank you, thank you. Yeah, stop me if I do something stupid. All right, so does that make sense then? So let's try another one. So the hard part is coming up with your cross-sectional area. It can be hard. It's the hardest part usually. Once you have your area, usually the integral is not that hard. The integral part usually is not the tricky part. The tricky part is getting the area function. So they have drawn, nice, thank you, the xy plane here. So they say the region bounded by the curve square root of cosine, that's not a curve you would be able to graph on your own. I would never ask you to graph that on your own. I'd give it to you if that was the function. On the interval 0 to pi over 2. So we're trapped in the first quadrant right there. That is that's our base region. So now we're going to put some sort of geometric shape on that base region. Got that base region, it's in the xy plane. Now we're going to stack next to each other squares, triangles, circles, whatever. Let's see what they say. Okay, so they say a solid of revolution is obtained by rotating r around the x-axis. So that creates this. So what is each cross section going to be?
Circle.
Circle or a disk, right? If we take that region R, rotate it around 360 degrees, we get this shape over here. It looks like a bullet head. Each cross section is going to be a circle. Whenever you do a rotation, if you take a region and you rotate it about an axis, your cross sections are going to be circles if the region is touching the axis of rotation. If the region's not touching the axis of rotation, you're going to get things called washers because there's going to be a hole in the middle. We'll get to that later. But this is touching the axis of rotation, so when it spins around, it's going to create cross sections that are disks. All right, we know what the area of a disk is. What is the area of a disk?
Pi r squared.
So area of a disk is pi times r squared. All right. So we look over here. What is the radius of our disk?
Square root of cosine.
Yeah, square. It's the function, right? This red line here is representing the radius of the corresponding disk. The radius is just the function. So that function is giving us the radius. So then we're going to deal with pi. The radius is root cosine x squared. So now we have our area function. That now tells us the area of all the disks for all the x's that are between 0 and pi over 2. Is the biggest disk at the left or the right for this region? The biggest disk is where the radius is biggest, and that's going to be on the left here. And what is the area of a disk of radius 1? Pi 1 squared? Pi r squared, r is 1, then you get pi. So the radius of this disk here on the left is 1. Excuse me, the radius is 1 and the area is pi. So the radius is 1, the area is pi. So, and what's the x value that corresponds to that disk?
0.
0.
Pi over 2.
So if we plug in 0 right there, cosine of 0 is 1, we get pi. So that area function is working so far. If we plug in x equals 0, we're getting the area of a circle of radius 1. How about at pi over 2? What should the area of the disk at pi over 2 be?
0.
It's just a point. So there's not actually going to be a disk when you do the rotation. So that area should be 0. Let's check. If we come to our area function and we plug in pi over 2, what's cosine of pi over 2?
0.
0. Cosine of pi over 2 is top of the unit circle. X value is 0. So we get 0. So that's usually enough. When you build your area function, check at the two endpoints, see if it makes sense. And then you're most likely you have the right area function. So volume is the integral of area. So if we integrate area, we are going to get volume, and we're integrating from 0 to pi over 2. So this, again, right here is area, and this right here is thickness. So the whole thing is representing a slice. So you can think of it in two ways. Integral of area is volume, or create a slice and add them all up to get the total volume. All right, so now the pi can just pop to the front. And then what is the integral of cosine? Sine. Integral of cosine is sine because the derivative of sine is cosine. So we end up with pi sine. And that's going from 0 to pi over 2. Sine of 0 is 0, so that's not going to contribute. And then what's sine of pi over 2?
Pi.
So pi over 2 is up here. Sine a second, 1. So that gives us a volume of pi cubic units. Not a whole number this time. So, irrational volume. Pi is everywhere. So building the area function is the hardest part. If you can find your area, the integral piece usually is not too bad. So we have to just sort of be able to build our cross-sectional area. Let's take a look at. So this, let's see if it loads. I should have checked before class to see if it loads. So this GeoGebra app should just show us kind of, you can get in there and fiddle around with it. And I just sort of created something to give you a visual of how these slices are moving through the solid object. I'm not sure how much manipulation, I should have checked that. Okay, so let's make some of these things a little more transparent. So we've got this wild looking shape, and you can see that these this is just sort of showing you how the cross sections are going to go through the region. And so if we can build the area function, you can just think of each one of these x values creating a different cross section. We're basically adding all of those slices up to get the total volume. And now this one I built with this upper curve and that lower curve. If we look at this example here, we can actually come right in here and type, and we can change that so that the upper curve looks like 2 minus x squared, if I'm reading that right. 2 minus x to the 2, and then the lower curve is x squared. So let's hit return. So then it just changed it. I should be able to zoom in a little bit. It seems to be a little finicky. And so this is the one that's up in that problem that we're going to find. So there are cross sections moving throughout it. You should be able to zoom in on this. I'm not sure why it's not getting bigger when I zoom in. But at any rate, you can play with that. So that gives you a visual idea of what we're doing here. So let's take a look. And sometimes it's not clear what your shape's going to look like. So this says the solid whose base is the region bounded by these two parabolas. So that's that green region down in the xy plane. That's the base of our solid object. It's down in the xy plane. And then we need to know, well, what geometric shape are we going to stack on that base? So then it says the cross sections, so that's the geometric shape that's going to be stacked on our base, cross sections through the solid perpendicular to the x-axis. Not perpendicular to y. They could tell us perpendicular to y or perpendicular to x. So they're saying perpendicular to x, so that's why this red line is perpendicular to x. And they're squares. So when you think about that, if you don't have these two pictures here, and you think about stacking all of these squares next to each other, it's not totally obvious that this is going to be the shape. Like when you imagine all those squares stacked next to each other, it's not necessarily clear, at least in my mind, that you're going to get a nice smooth cap to it like that, right? You're going to get this sort of parabolic cap that's nice and smooth across it. Not totally obvious, which is why it's nice to have some technology. So let's go ahead and find the area. So the area of our square, since they told us cross sections are square, will be base times height or whatever, base squared, side squared, however you want to think of the area. And what is the length of this base? Well, we've got this upper curve and this lower curve. Yeah, it's upper minus lower. So it's going to be the upper, which is 2 minus x squared, minus the lower, which is just x squared, and then all that squared. That's going to be the area of the square. Let's simplify this. So it's going to be 2 minus 2x squared all squared. And if we square that out, we're going to get 4x to the 4th minus 8x squared plus 4. We FOIL that all out. Okay. Let's figure out what our limits of integration are, right? They didn't tell us that here. We can't check our two extreme points or anything until we know what our limits of integration are. What do we do to find the limits of integration? Set them equal to each other. So we're going to set x squared equal to 2 minus x squared. Oh, nonlinear. Everything to one side and factor. Although this is one of those cases where you actually could put letters to the left and numbers to the right. You could.
How do we know that the 2 minus x squared comes first?
Because that is the top curve. If we were to draw this in the xy plane, the 2 minus x squared, negative x squared opens down and then it's shifted up. So the board is very jumpy. So the parabola is opening down. That's the upper curve. And then y equals x squared is going to go that way. So y equals x squared is the traditional parabola. Y equals negative x squared flips it but then shifts it up. So that one's going to be on top, which is the 2 minus x squared. Right, here's the y-axis right there. So the y-axis, when we do the three-dimensional, when we do the three-dimensional graph, the y-axis is that way.
Okay.
X-axis is coming out of the board.
Yeah.
So it's a little disorienting.
Yeah, I didn't realize that was the.
Yeah, that's the y-axis. Yeah. I should have pointed that out. So this is 2x squared equals 2, which is x squared equals 1. So this is a quadratic, a nonlinear, that you don't have to put everything on one side and factor. Generally, putting everything on one side and factoring is the safest play. But in a simple case like this, you wouldn't have to do this. You could, of course, take the square root of both sides. But we will get negative 1 and 1. So what is the area of the square at those two extremities? When x is -1 and x is 1, what should the area of the squares be? So if we're right here, what's the base length of the square? Aren't these base lengths getting closer and closer to 0? Right? As those curves come together, the distance between the curves is becoming 0. So at this extreme value over here where x is +1, we should have an area of 0. And on the other side over here when x is -1, we should also have a square with area of 0 because it's just pinching down to a point. When we plug in 1 or -1 here, do we get 0? So if we plug in 1 or -1, we have an even exponent, so it doesn't matter. We're going to get 4 minus a plus 4. Yeah, we get 0 for both of those extremes. And what is the x value for the largest square? What x value, if you look at that picture up there, what x value is going to generate the biggest distance between those two curves?
0.
X equals 0. So if we come over here and plug in x equals 0, we see that that biggest square has area 4. And that's going to be the one that's like sitting on the y-axis where x is 0. That's going to be the biggest square. Okay, so then once we have our area function, then we just have to integrate. And we said -1 to 1. Now, could we use symmetry here? Is there symmetry here around the y-axis?
Yes.
For sure. Right? These two parabolas are both symmetric about the y-axis, so we could do this. We could say, hey, we prefer to have a limit of integration that's 0. So we could say, let's not do that, let's do this. And use a symmetry 2. And because this region in here has the same area as that region over there. So our solid could be chopped in half. So we could do that. You don't have to, though, of course. If you're not seeing that symmetry, you don't need to jump to it.
So when there's a symmetry, you will change only the bottom of the integral?
It depends on the picture.
Oh.
Depends on the picture. So,
Oh, like if you're choosing either one of those sides.
yeah, so it depends on what the limits of integration are. But yeah, we'll see different things. But having a 0 as a limit of integration is always nice. All right, so we're going to integrate here. We're going to get 4/5 x to the 5th minus 8/3 x to the 3 plus 4x if I integrate it properly. 0 to 1. 0 is a non-contributor to the volume. So all we have to do is plug in the 1 and deal with some arithmetic. So we have 4/5 minus 8/3 plus 4. So before we add those together, is there any part of that that you want to ask about? Any part that's not clear? So again, our main principle, find the cross-sectional area and then integrate it. That's our main principle. So then our final answer, we're going to get a common denominator of 15. So multiply that one by 3, multiply that one by 5, multiply that one by 15, and then our common denominator will be there. So that's 20 plus 12, that's 32. Doubled is 64 over 15. The factors of 15 are 3 and 5. There's no 3 factor in 64 and no 5 factor, so that's our simplified answer. Everyone know how to tell if a number is divisible by 3? Sum of the digits, if the sum of the digits is divisible by 3, then the number is divisible by 3. So the 6 and the 4 add to 10, that's not divisible by 3, so 64 is not divisible by 3.
Say that one more time?
Yeah. If you want to know whether a number is divisible by 3 or 9, add the digits, and if that new number is divisible by 3 or 9, then the original is divisible by 3 or 9.
Just the number?
Yeah, because the denominator we know factors into 3 and 5. So if there's any simplification, there would be a canceling of a 3 or a 5, but the numerator is not divisible by 3 and it's not divisible by 5, so we know it's not.
So if it's like 63 instead,
Yeah,
that's 63.
so 63 would be divisible by 3, so we can cancel out 3. Correct. You know when a number is divisible by 7? Chop off the last digit, double it, and subtract it from the front digits, and if that new number is divisible by 7, then the original is.
Damn, I was supposed to do
We'll talk about that later.
I'm hungry though.
That's hard to conceptualize. All right, well, have a great weekend. Do a ton of math. Maybe that's not the right unit. Ton. Do a lot of math. Do endless math problems. Have a great weekend. Be safe. Have fun.